Lesson 12.4 is all about multiplying probabilities. This is going to come into play a lot when we're using one event and another event, or one event or another event. These are instances when we'll need to multiply different probabilities together. So when we are looking at examples with two independent events, again, an independent event is when one piece does not affect the other. It's independent of the outcomes of the other events. So, let's look at the example. I'll show you what it means. Gerardo has 9 dimes and 7 pennies in his pocket. He randomly selects one coin, looks at it, and replaces it. Because he replaces it in his pocket, that makes it independent. Because he's not actually changing then the outcome of the other, his next draw. He still has just as much chance to draw the same coin again next time. Now that he has replaced it into his pocket, he then randomly selects another coin. What is the probability that both of the coins he selects are dimes? So again, looking at multiplying probabilities, if we want the probability of a dime and a dime, that would be the same as saying probability of dime and dime, in which case we do what's the probability of a dime times what's the probability of a dime. So if we have 9 dimes and 7 pennies, that means in total, 9 plus 7, there are 16 coins in Gerardo's pocket. So the probability of drawing a dime, suppose I should look at this one, would be 9, because there are 9 dimes out of 16. So if we want the probability of a dime and a dime, so dime times a dime, we'd say 9/16 times 9 over 16 again. Because again, they're the same, they have the same probability. Each time when he draws into his pocket, there are 9 dimes and a total of 16 coins. So that's going to leave us with 81 over 256. That would be his probability. Moving on from there, if we have 3 independent events, so when 3 dice are rolled, what is the probability that 2 dice will show a 5 and the third dice shows an even number? Well, so we want the probability of A and B and C. So we need the probability of A times the probability of B times the probability of C, in which case our probability is 5, 5, and an even number. So we want probability of rolling a 5, probability of rolling a 5, and probability of rolling an even number. Probably get rid of this. Oops, throw it down there. So what's the probability of getting a 5 on a dice? Well, if we have 1, 2, 3, 4, 5, and 6 are the faces of a dice, those are the only ones we can get. It'll only happen one time that we get a 5, so we'd say 5, or oops, I should say there's only one way to get it, and there are a total of 1, 2, 3, 4, 5, 6 possible rolls that you can get. So the probability of rolling a 5 is 1/6. So we've got 1/6 there, and actually I want to give us another one because we have probability of rolling a 5 and probability of rolling another 5. So multiply those. Multiplied by, what's our probability of rolling an even? Well, it looks like 2, 4, and 6 are even. So we have 3 out of a total of, again, there are 6. So we could say 3/6, or if we reduce that down, we have 1/2. So we take our 1/2. Well, I don't need that equal sign. Might as well come along with, though. So 1/6 times 1/6 times 1/2 is going to be our probability in the end. That's going to give us 1 over 72. So 1/72 is our probability that we will get 2 fives, and an even number. Now we'll look at the probability of dependent events. Remember, these are events where one event will affect another one. So if in our last example, Gerardo did not replace the coins in his pocket, that would no longer be independent, because then the next time he draws out of his pocket, there are less coins. So it's going to affect his probability. So in this example, it says a host of a game show is drawing chips from a bag to determine the prizes for which contestants will play. Of the 20 chips, so there are 20 total, 11 say computer, 8 say trip, and 1 says truck. If the host draws the chips at random and does not replace them, that's why we are making it dependent, because they're not being replaced. Find each probability. So if we want a computer, then a truck. Okay, so in this case, probability of a computer. Well, we have 11 chips that say computer, and there are 20 total. So the probability of a computer would be 11 over 20. But then after that, we're looking for probability of getting a truck. And there are only one chip that says truck. But in this case, after we've drawn our 20, or drawn from our original 20, now after we drew the one that hopefully had computer, now there are only 19 chips left to draw. So instead of being 1 out of 20, the probability now is only 1 out of 19. So in this case, 11 twentieths times 1 over 19 is going to leave us with 11 out of 380. So in this case then, we could reduce that down. Well, I'll just say it in something else. In decimal form, it would be 0.029, or we could say 2.9%. There's a 2.9% chance that the chips will say computer, then truck. Let's say we wanted 2 of them to say trip. So he draws 2 and they both say trip. Our first one that we draw, there are going to be 8 chances for it to say trip, because there are 8 chips that say trip on them, and there are 20 total. So it would be 8 out of 20. In our second chance, our second draw out of the bag, there are now only 7 left that say trip, because we've already drawn one, remember? That's what or at least we were hoping to have already drawn one that says trip on it. And there are no longer 20, there are only 19 again. So in this case, we would have 56 over 380, which in this case we can actually reduce down to 14 out of 95. Or if we wanted to say that as a decimal, we could say 0.147 or 14.7%. So there's a 14.7% chance that when we draw 2 of them, they will both say trip. Pretty neat. So now we're going to look at 3 dependent events all happening at the same time, or should I say consecutively, one after the other. So in this case, we are drawing 3 cards from a standard deck of cards without replacing them. Again, the fact that we're not replacing them is very important. We're looking for the probability of drawing first a heart, then another heart, and then a spade in that order. So again, it looks like the probability of heart, heart, spade. Well, let's look at the first heart. So we'll say H sub 1. There are 13 hearts in a standard deck. Ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, Jack, Queen, King. So 13 in total. And we start with a total of 52 cards. So 13 out of 52 will be hearts. So that is our probability of drawing our first one as a heart. Probability of drawing our second heart. Well, if we've already drawn a first one over in our original first try here, we've already drawn one, so now there are only 12 hearts left, and there are only 51 cards that we are dealing with. So our total hearts went down and our total cards went down. So this time we're only doing 12 out of 51. Then our last card that we want will be a spade. And so if we want to get a spade, there's still 13 total spades left because we haven't drawn any. Remember, we just want to talk about before drawing only the hearts. So if we haven't drawn any spades yet, we still have 13 chances to draw them. But there are now only 50 cards left because we already drew one over here and our second one over here, first and second. Now this is our third. So there are only 50 cards left. So 13 over 52 times 12 over 51 times 13 over 50. In the end, that's going to leave us with 2,028 over 132,600. So that would be our probability of drawing a heart, heart, and then a spade. Remember, if there are any questions on probability of dependent or independent events, make sure we are asking those questions. Otherwise, stay golden.